Okay, this is section 8.1. This section and the next two sections, we're going to be solving systems of two equations. And we're going to do this three different ways. We're going to do it by graphing, by substitution, and by elimination. Okay? So we're going to be doing the same thing over and over again, just different ways. And here's the best part. Once we're done, you just pick your favorite and roll with it. That's kind of the nice part about this, is that, and I'm going to tell you what, your favorite is not going to be graphing. I guarantee that. So the word system just means that there's two equations being solved at the same time. That's all that means. Now, what do I mean by the solution to a system? Well, the solution to a system of two equations is the point of intersection. So when I say solution, I mean the point of intersection of two lines. Okay? Now, there's three types of solutions. When you think of two lines, remember from the last thing, those two lines can either touch or not touch. So here, they touch. Here, they don't touch. Now, there's a third option that we didn't really talk about in the last section. That third option is, what if the two lines are exactly the same line? Right? They touch everywhere. So here's the three types of solutions. There's one point of intersection. Okay, so there's my first one. One point of intersection, one solution. Hawkes refers to this as consistent. The two lines can be parallel. Parallel lines have no point of intersection, so there's no solution. See, one point of intersection, one solution. No points of intersection, no solution. Hawkes calls these inconsistent systems. And then what happens if we have the same line? Hawkes calls this dependent, and that's because you get an infinite number of intersection points and an infinite number of solutions. So what we're going to have to do with these dependent systems is not much, really. We're just going to have to label them as dependent and just recognize that, hey, there's an infinite number of solutions because they're the same line. That's about it. Okay. Now, to solve all of these by graphing, unfortunately, we're going to have to put them in this mx plus b form first. All right. Now, these are going to be kind of messy, right? Because you have to graph and then you have to look for the point of intersection. Now, this is going to be a lot easier in Hawkes because you're going to have that grid. So I don't have a nice grid paper for you on short notice here, so I'm going to do the best I can with what I got. So solving this for y, I'm going to subtract x from both sides, and I get this. So now both of these are in y equals mx plus b form. So I've got the top equation, the 6 minus x, my bottom equation, x plus 4. So I just kind of, did those separately. Said, okay, look, here's my intercept. Here's my slope of -1. Here, the slope is 1, the intercept's 4. Notice these are kind of backwards. Right? This one, the constant's first. But in both cases, the constant is my y-intercept, or the b value for the y-intercept, and the coefficient of x is my slope. So that's what's consistent. So then I graph these lines individually. All right. This line, remember how to graph. We start at 0, 6, right here. From that point, we go down 1 to the right 1. So down 1 to the right 1. I end up at the 0.15. So connecting that, there's one line. This one, I start at 0, 4. Boop. This slope of 1 over 1 tells me to go up 1 and to the right 1. Oh, and I happen to end up at that exact same point. So where do these two intersect? They intersect at one point, and that point is 1, 5. So we say that the solution to this system is the point 1, 5. Remember, the solution is a point, not a single number. Now, we can check these answers, which is pretty awesome. So if you wanted to check that the 0.15 is a solution for this system, we need to plug 1 for x and 5 for y into both equations. And both of those equations should be true. Now, what do I mean by true? Well, let's plug in 1 for x and 5 for y. So we get 1 plus 5 equals 6. Is that true? Yep. 5 equals 1 plus 4. Is that true? Yep. Both of these have to be a yes in order for that point to be the solution of this system. Remember, the system is both equations. So looking at this one, is 0, 4 a solution to this system? Well, let's plug in 0 for x and 4 for y. Is 4 equal to 0 plus 4? Yeah. Is 4 equal to 2 times 0 plus 1? No. If you get a no, then this point is not a solution. That means that these two lines do not intersect at 0, 4. All right. So let's talk about solving these. So here's where this gets a little messy, okay? The worst part of this is, of course, the graphing. But these, you got to get these in y equals mx plus b form in order to graph them. So I'm going to do this in column form. So here's my top equation. Here's the bottom equation. So this is just me doing the algebra to get to get these into y equals mx plus b form. So when I add 3x to both sides and then divide both sides by 3, remember I got to divide each of those terms by 3, I get this form over here, moving that x term over and then dividing by that coefficient of y. Now, check it out. These look almost identical, but they're not. That one's a negative, that's a positive. Look at the slopes on both of them, though. The slopes on both of them are 1. Same slope means parallel lines. Parallel lines never touch. So, if they're parallel lines, there's no solution. That means no points of intersection. Remember, solution means points of intersection. That's what Hawkes calls inconsistent. Now, I just put a little note here about the graph in Hawkes, because if this, when this is in Hawkes, you would just have to put those equations in there and it would graph them for you. So I pulled this example right out of Hawkes. So you would just have to type in the equations, it would graph it, and you could look at them and say, oh yeah, those are parallel, those aren't touching. Okay, lastly, we have yet another system here. We got to put both of these into y equals mx plus b form. Whew, you're going to get a lot of practice with this. So again, top equation, bottom equation, moving the x term over, dividing by the coefficient of y. Move the x term over, divide by the coefficient of y, simplify. Look, those two lines end up being the exact same line. So even without graphing it, I can tell that these two lines are identical. Therefore, we'll have an infinite number of solutions, or is what Hawkes calls dependent. Now, what Hawkes is going to have you do for these is, it's probably, a lot of times it'll have like a box for you to put the answer in, or it'll have like a little circle over here where it'll say inconsistent or dependent. So if you get a solution, like say you get the answer of 1, 5, then you just put 1, 5. But if you get their parallel, boop, you put inconsistent. You just click on that, you're done. If, like this one, you get the same line, then boop, you click on dependent and you're done. So, okay, I know that was short and sweet, but that does conclude this section 8.1.